Good afternoon. Welcome to the second session after lunch. And today this session is about grid integration, optimization, and technology advancement. When we talk about renewable energy or any kind of it, chain is strongest at its weakest link. And when we talk about sustainable energy, creating alternate energy sources, grid optimization, integration is one of the link which has not been focused a lot. So today we are going to talk and learn about some of the new advancements and some of the very wonderful ideas that have come across from industry and academia. So without further ado, I invite our first speaker, Dr. Saurabh Mishra, Assistant Professor from Center for APJ Abdul Kalam University, to talk about the first topic. Saurabh, welcome.
Thank you, sir. Respected session chair, respected speakers, and respected delegates and fellow researchers. It is great privilege to be here at IEW to present my research work. So, today I'll be sharing my research work on the nature-inspired photovoltaic material where we combine the chlorophyll extract from the plant leaves and the TiO2 nanoparticles to create new novel stable solar absorber. And this research is the intersection of renewable energy and material science and the biomimicry. So I'll be start with the objective of my study, then the experimental analysis, and then the results and discussion, and finally the conclusion. Right. So traditionally we were like our energy needs were dominated by the fossil fuels, which are very very finite and environmentally damaging. But as we transition toward the sustainable future, this renewable energy, particularly the solar energy, can offer the clean and abundant and sustainable alternatives. So my main topic was to target was to develop a new material for the photovoltaics. As we know that India imports silicon, like we are totally dependent to the silicon, and then we move to the perovskite. But those are having certain limitations. So I used this Mother Nature, because Mother Nature have already mastered this solar energy harvesting through the photosynthesis, and the plant use the chlorophyll to absorb the solar energy and convert the solar energy into the chemical energy, and means it offers a tremendous efficiency in converting solar energy into the other energy, the energy conversion. So here I took some ideas, and I wanted to focus on the chlorophyll. But chlorophyll has certain limitations on its charge mobile carrier mobility, charge carrier mobility, and the instability. So what we did, we just combined the nanoparticles with this chloroform structure, or we can say we dope this chlorophyll with the nanoparticles and created a new hybrid solar absorber material. So our primary objective was to develop a new solar absorber material that is stable and pretty much efficient than the other. So the first objective was to extract the chlorophyll from the plant leaves, and then removal of central magnesium ion from this chlorophyll material, and then it incorporating the nanoparticles into its chain, and then characterize, because we have developed the material, so we need to characterize it. So characterization of that material, and then after we have gone for the simulation using the Augma Nano software. So this was the entire workflow, right? From selection of the plant leaves, we used people leaves. Uh, this is the entire workflow from selection to the development, the hybrid material development. So in the first step, we have selected or collected the plant leaves, and then we have crushed it and dried and then grounded using ethanol as a solvent. Ethanol, what ethanol did? Ethanol just break down its plant cells and dissolve the chlorophyll without degrading its molecular structure, right? So and this chlorophyll was stored, filtered and stored, in controlled condition to preserve its optical properties. So this step was so crucial because we are just going to replace this magnesium ion from the center of porphyrin ring, because this step is crucial because this system will give a platform for the nanoparticle interaction to this porphyrin ring. So here we used acid-base demetallation step. After the demetallation, we just prepared the nanofluid solutions and incorporated this TiO2 nanoparticle into the porphyrin ring and successfully developed the TiO2 doped chlorophyll hybrid material, and which was so stable that we will see in the characterization. So overall experiment process was this. Now the material was developed and we were on to the characterization process. So we utilized FTIR, FESEM and UV visible spectroscopy and the other one to characterize this material. So here is the FTIR spectroscopy. In FTIR spectroscopy we can see there are certain stretching and vibrations of the C double bond O and COC that confirms the chemical compatibility of this hybrid material with the TiO2 nanoparticles and the stability, the stable bond. These stable bonds confirms the charge transfer process, right? So again we have gone for the UV visible absorption spectroscopy. So UV visible was important. Sorry. UV visible was important because we want to check about like how much light harvesting capacity it was having, this hybrid material. So from this UV visible spectroscopy we can see that there was a tremendous shift to this hybrid material have tremendous shift toward the visible spectrum, that is from 300 to 700 nanometer. So it was having this absorption capacity, light absorption capacity. So it was like it was good for the solar fabrication. Again we had gone for the X-ray diffraction. This was to analyze the crystalline structure. So you can see those peaks, those XRD peaks confirms the anatase phase of TiO2. Anatase phase of TiO2 that confirms the charge transfer, charge generation actually in this hybrid material, right? Again, when we have gone for the torque plot, so it was having the reduction of the band gap of from 2.41 electron volt to 2.2 electron volt. And for the solar fabrication, it is reported that like if the band gap lies between 0.7 to 3.2, we can go for the solar cell fabrication. So XRD again confirms the crystallinity, right? So again, we have gone for the morphology because surface structure is very important if you are going for any material, right? So in TiO2, in pure chlorophyll, we can see the flake-like structure and porous. It was porous and irregular. But when we combined, when we have incorporated these nanoparticles into the chlorophyll structure, we had the uniform distribution of those nanoparticles on the surface and the porosity also. So these nanoparticles give the tremendous surface area which can support the charge transfer effectively, right? Again, now if we are talking about the solar energy, this is the electrical analysis is very important. So we have gone for the 4-probe electrical analysis, and this electrical analysis confirms the ohmic behavior of this hybrid material. And again, we have gone for the temperature dependent resistance measurement. So it is having the negative value of that. It means this hybrid material was also semi-conductive in nature, right? See, the chlorophyll is also a semi-conductor material, but again, when we are incorporating some nanoparticles like TiO2, the semiconducting behavior was improved, right? So this was the thing, we have gone for the simulation process because we have the material, we have the band gap, we have all the properties. So we have gone for the simulation study where we used indium tin oxide as a top electrode and fullerene as a electron transport layer, and this hybrid material as a absorber layer, active layer, because we have developed it for the absorbing the photons from the sunlight, and P3HT as a whole transport layer, and again the bottom electrode is the silver we have used. So we have gone for this this simulation, and we have got tremendous efficiency up to the 41%. So this was the simulation, and we have gone for the fabrication also, and again the fabricated device has given us the efficiency of 43%. So this was the again a milestone in the research, and we have patented this technology. So again, we have gone for some characterization like CV analysis, FP analysis, and current density and voltage analysis. So all these analysis confirms that there is more and more less recombination losses and the more and more low resistance and the high conductivity. So these results confirm that this developed hybrid material can offer a sustainable stable structure to the solar cell. Thank you so much. So this was from my side. Thank you.
Thank you, Saurabh. Our next speaker is Sachin Kumar Agarwal from Engineers India Limited, and he is going to talk about decarbonizing offshore operations.
Good afternoon to everyone. First of all, I would like to thank you, IEW and EIL, for giving me an opportunity to represent my paper on the decarbonization offshore operation through renewable energy integration and hybrid microgrids. In my presentation, I will try to cover following points that you can see in my presentation also: introduction to offshore decarbonization, then next methodology and assessment framework, renewable energy technologies, hybrid microgrids and energy storage. Then I will try to discuss some case studies and global learning, and then we will go through Indian offshore feasibility, and in the last I will conclude and will give the recommendation for the offshore industry. Why decarbonizing offshore operations? Our offshore oil and gas platforms are very high energy intensity 24/7 operation of gas turbine generator is required, which requires a continuous fuel supply also. Diesel generators, and there is a high carbon footprint per barrel. And there is a global climate mandates also, like Paris Agreement, Conference of Parties, COP, India's 2070 net zero commitments, costly fuel logistic in the offshore platforms, and rising operation expenditures. And there is an aging conventional power systems also. Our existing offshore platform power architecture you can see here, it's typically powered by the gas turbine generator, which requires the continuous fuel supply, diesel generators, solar panels, and thermoelectric generators on the unmanned platforms. What are the issues with the existing power system architecture? There is a high maintenance frequency, emission intensive, and requires the continuous fuel supply. What are the emerging opportunities in these offshore fields for the renewable energy? We have the floating offshore wind energy, then offshore solar panels, wave and tidal energies, digitalized microgrids, energy storage. This can create pathways for the clean offshore operation. I will try to discuss these technology in the next slides. What are the objectives of my presentation? I will try to assess the feasibility of the integrating renewable energy sources like wind, solar, wave and tidal energies. Evaluate hybrid renewables plus conventional systems. Will perform the techno-economic analysis of the various renewable energy available. Then we'll give the rank renewable energy technology using the MCDMM. We will identify decarbonizing potential and benefits, and will provide the roadmap for the offshore India. Techno-economic assessment framework for the renewable energy integration. These tools covers the technical performance, operational reliability, capex and opex modeling, environmental impact, integration challenges, scalability and life scale economics. What is the MCDMM tools? These tools used for the fuzzy analytic hierarchy process that will assign the weightage importance to the design criteria, and the TOPSIS. TOPSIS is a technique for order preference by similarity to ideal solutions that will provide a rank to the various renewable energy available in the market. We are evaluating the various criteria like the reliability and availability of the renewable energy, capex and opex required for the renewable energy implementation, greenhouse gas reduction, retrofit complexity, and safety and maintainability. Offshore energy demand profiling. Our typical offshore platforms are require the power supply for the power processing offshore platforms, drilling rigs, utility system like HVAC, pumps, compressors, etc. Our living quarter blocks, safety critical loads for the DCS, ESD, FNG, and telecom, SCADA, etc. So we have to consider the various profiles like the base loads, peak loads, and intermittent drilling loads required during the offshore platform operations. Let us go through some technologies available for the renewable energy in the offshore platforms. Like the floating offshore wind turbines, this can be deployed in the more than 60-meter depth of the offshore platforms, because we cannot fix the platforms for the wind turbines, and this will provide a high capacity factor near about 45 to 55%, and this will create the minimal seabed disturbance also. Let us go through the offshore solar technology. These solar technology can be mounted on the top side or floating pontoons and will create the power supply. This has a medium maturity level and then can support the midday peak saving also. This will provide the complements to the winds as well as solar during the calm periods. Wave and tidal energy, it's the very latest technology and it's a very high predictable during the tidal cycles, especially for the monsoon periods. Wave energy available during the monsoon period, this is still maturing technology and a strong candidate for the hybrid renewable energy integrations. Next one is the hybrid microgrid architectures. In this we can integrate various wind, solar, marine and battery energy storage system and existing conventional gas turbine generators together, and then can generate the power supply and will integrate in the existing microgrids also. By this we can load balancing we can do dynamically, can reduce the spinning reserve requirements and can enable the renewable energy fast dispatch to our offshore platforms. What are the typical capacity factor for the various renewable technology available? Like in the wind, we are getting the maximum capacity factors. It's more than 50%. In the solar technology, we are getting the capacity factor near about the 20%. And in the wave and tidal energy, we are getting the less than 10% capacity factors. What are the various energy storage options on the unmanned platforms or offshore process platforms? Like the battery energy storage system, we are getting the fast response and we can save the money also and can give the spinning reserve replacements. In the hydrogen storage, we can convert the excess renewable energy into the hydrogen and can store the energy for the multi-days. And that is excellent for the future decarbonization of the offshore platforms. Digitalization and automation, this is the latest trending technologies like the digital twins for the real-time energy optimization, energy management system with the predictive algorithms, automated load shedding logics we can create, remote monitoring we can do from the onshore also, and we can provide the diagnostic to the our renewable energy integration sources, and will support the unmanned platform operations. Let us go through some global case study. In the North Sea, they have the floating wind powering offshore assets, and this will give the capacity factor more than 55% and fuel burn reduction up to the 70% and can reduce the generator maintenance also. And there will be very low carbon exposure. Four European countries like the Belgium, Denmark, Germany, and the Netherlands have the place to generate the more than 150 gigawatts wind capacity in their waters by the 2050. In the Gulf of Mexico, they have the hybrid solar plus wind microgrids, and that will reduce the diesel consumption by the 30% and payback period is the less than 7 years and will improve the uptime and reliability also. What are the feasibility for the offshore India? In the wind source, if you can see the west coast, it's excellent for the floating offshore wind turbines. East coast is the moderate, but in that we can implement the hybrid microgrids. In the solar, very high readings in the India, limited structure space on the platforms, that is a constraint for the solar technology. For the marine technology like wave and tidal energy, it's a site specific in the Gujarat and Andaman. It's a very best suitable place for the wave and tidal energy. What are the emission reduction potential for a 40 megawatt offshore platforms? Floating offshore wind turbine hybrid can reduce the carbon dioxide reduction by the 25,000 to 45,000. Hybrid microgrids can give the 30 to 55% reduction in the fuel uses and can provide a significant reduction in the carbon credit purchase. And there is a very less maintenance issue also. Let us go through some comparison between the conventional system and the renewable integrated hybrid systems. By using the renewable energy integrated hybrid system, we can reduce the diesel and gas consumption by the 30 to 50% and carbon dioxide emission by the 40 to 60% we can reduce. Operating expenditure we can reduce by the 25 to 35% and payback period is approximate 6 to 8 years. And by this we can comply the carbon mandates also. What are the various challenges to implement this renewable energy integration in the offshore platforms? In the offshore, we have the very harsh marine environment and very corrosive also. And there is a logistic and installation complexity for the offshore platforms. Initially, we have the high capex and retrofitting legacy offshore infrastructure. And there is a limited deck space for the solar and battery energy storage system on our offshore platforms. So these are the constraints for the renewable energy integration for offshore installation. But what are the enablers? Like the maturing floating wind technology, and there is a falling battery prices day by day, and there is a government push also for the renewable energy and offshore developments. Carbon credits revenue streams, advance in the smart controls and digital twins. So these are the enablers for the renewable energy integration in the offshore platforms. You can see the implementation roadmap phase wise for the renewable energy integration in the offshore platforms. First, we have to do the screening and profiling, then resources mapping, then we can do the concept development for the floating offshore wind turbines or hybrid, what are the required, and then we have to do the detail engineering, and then in the finally we can deploy and monitor. What are the key findings? Offshore wind is the most viable due to high reliability, scalable and consistent resources. Solar and marine can complement resources in the hybrid systems. Hybrid microgrids is a more reliable and emission reductions. Energy storage and digital twins, it's a system resilience and predictive control can improve the reliability also. Return of investment can be achieved by within the 7 years. This is the conclusion of my presentation. Decarbonization of offshore assets by renewable integration is technically feasible and economically justified also. Floating wind plus hybrid microgrids can offer the optimal solution. Digital twins and energy storage enables the high reliability, can support the India's net zero 2070 goals, and can enable the long-term cost saving carbon credits. What is the way forward? Pilot renewable energy hybrid demonstration for the Indian offshore assets can scale up by the policy supports and carbon trading mechanism. We can integrate the artificial intelligence, digital twins and hydrogen storage together, and we can collaborate between the oil and gas operations consultants, various EPC and renewable energy developers together. And by that we can implement renewable energy integration in the offshore platforms. This is all total on behalf of me. Thank you. Thank you very much.
Thank you, Sachin. Now that brings us into the third topic, and that's about real-time framework for renewable energy, led by Saket, Kumar Mishra. So Saket, over to you.
Hello, Namaskar. Good afternoon, respected leaders, delegates, and my dear friends. I am Saket Kumar Mishra, Aspire Associate at Baker Hughes. Today I will present our work title, as sir told. In short, is the hybrid smart microgrid for sustainable industrial power system. This research carried out by me and my co-author, Mr. Arun Kiruvakaran, who is present here today. And coming to our topic, we all know that India is undergoing a rapid energy transition under strong national commitments such as National Green Hydrogen Mission targeting, we are targeting 5 million tons per year of green hydrogen production by year 2030, renewable capacity target 500 gigawatt by year 2030, and net zero carbon emission commitment by year 2070. And in this way, some state governments also taking initiatives to support our central government, and Tamil Nadu, one of the leading state in our country with more than 20 gigawatt renewable capacity, and that renewable capacity is coming more from wind energy, and it is continues to expand industrial corridors like SIPCOT. And however, renewable intermittency causes reliability problems for continuous process industries such as manufacturing and electronics assembly, where even minute of outages may result in lack of rupees of in losses. Therefore, industries need firm, low carbon and cyber secure 24/7 power, not just renewable energy. So here we all can see the solar and wind map of India. And due to availability of surveys and other meteorological data for already running SIPCOTs in Tamil Nadu and renewable energy data about wind generations, so this proposed study is focuses on deployment feasibility for the proposed SIPCOT cluster in Nanguneri, Tamil Nadu, and ultimately our goal is to align with India's net zero carbon emission 2070 mission and energy transition roadmap for industrial corridors. Our agenda and motivation behind this work is for need for reliable, secure and low carbon power in industrial clusters. Traditional grid supply suffers from uncertainty, outages and rising cost, as well as due to major generation of power from fossil fuels, more CO2 emission is there. Whereas renewable provide clean energy but are intermittent. So at SIPCOT Nanguneri, maximum demand of approx 50 megawatt of daily load is there. We proposing and studied a real-time cyber-secure hybrid microgrid integrating 50 megawatt solar from Etanakulam village in Undavalli district and 30 megawatt of wind from Arla Moli in Kanyakumari district. Both have a huge scope in solar and wind generations, and 60 megawatt are BESS is battery energy storage system, and a green hydrogen ready low emission industrial gas turbine. Here for study purpose we are using Nova LT16 of 16 megawatt, which is in-house made by our company Baker Hughes only for farming and emergency backup. And the other part is energy management system dispatch and cyber security model, with this objective to reduce grid import, minimize renewable energy curtailment, reduce carbon dioxide emissions, eliminate shortage hours, and strengthen our cyber resilience. And this model is replicable to all industrial corridors, data centers, and defense facilities around the globe, subject to availability of solar, wind, and green hydrogen. Going to the next slides, we have in the next two slides we have system architecture and methodology of our system. So this is the proposed hybrid microgrid architecture of our system. Here we have three layers. One is forecasting layer, second one is energy management system layers, and third one is cyber security layers. In the cyber security, in forecasting layer, we taking inputs from NASA power satellite data of last 1 year trends and local weather sensor, both used to train our model, and this layer is forecasting the next 1 to 7 days of solar and wind availability for the required location. Also, we are taking GHI data, which is global hourly irradiance for solar, and turbine deviations for wind generation for better calculations. And here we are using two models to forecast the day ahead power. So for statical prediction we are using Cerimex, and for learning seasonal and non-linear behavior we are using LSTM model. And our second layer is energy management system layer, which is managing grid import and export using the BESS for time shifting and peak saving, use of Nova LT16 gas turbine to ensure firming and continuity. So our EMS is also having one programming based optimization, which is mixed integer linear programming, which is using forecasting inputs from our forecasting model, which minimizing the cost and CO2 emissions. And the cyber security layer, which is nowadays very important for any smart grid and micro grid. So we are using isolation forest machine learning based intrusion detection model to detect 12 cyber attack categories. And it is also we are doing that physics based residual checks for solar and wind deviations. Our risk fusion engine that transition between safe island and lockdown mode based on detection of threats. We will see more about this in next slides. And this model together follows the philosophy of predict, optimize, and protect. It means predict in renewable generation using AI based forecasting, optimize dispatch through EMS integrating renewable, BESS, and gas turbines. And the third and most important for our power industry is protect the system using intelligent multi-layered cyber security mechanism. So here is one operational dashboard which we made. We developed a real operational interface using a secure access Python based Streamlit dashboard, which can be implemented in SCADA model in future. Here we can toggle running mode, adjust parameters, view SOCs and CO2 and grid performance, and export CSV and plots in our local drives. The secure login support role based access control, which is essential for industrial safety and supervisory control, is also provided here. Here we integrated 3 mode of access, which is operator, engineer, and IT. Operator can run the model and schedule any dispatch. Engineer can change parameters and control the technicality of our model, and IT can change UI design backend codes, which is currently running on Python and other IT related things. Our dashboard is showing forecast control panel with battery capacity, power limits, grid pricing, and emission parameter entry. It can run forecast function for day ahead wind and solar predictions, energy management control and dispatch, live monitoring of battery state of charge, grid performance, and dispatch schedule by EMS. So, this model also same dashboard can running on that IDS model of for cyber security threats. If any cyber security threat will come, it will give us a notification and alert, and it will cut that system from any external grid supply. So we will see more on this in the result sections. So here we have shown our forecasting results, and our accuracy of forecast is around 90 to 92%. Here you can see PV and wind forecast versus actual 14-day history with a 72-hour forecast window. The graph show 14-day actual solar and wind generation recorded historically combined with 72-hour forecast overlay. For solar generation, our MAP error is approximately 9.2%, and which means error is around 1200 kilowatt. If our model, forecasting model, is showing that we can generate 10,000 kilowatt in the next day, so we are subtracting 1200 kilowatt from that, and the rest 8800 kilowatt we are giving to our EMS model. So, and for wind generation, our MAP is this model MAP is around 13.6%, and that means around 420 kilowatts of error is there. So we are subtracting, if we are generating 5000 kilowatt, able to predict 5000 kilowatt for the day ahead, so we are subtracting 420 kilowatt from that, and that the rest around 4600 we are giving to the model. And our EMS model is here, and our under baseline condition, our grid import is around 7,200 megawatts, which is basically coming from fossil fuel and coal dominated grid only, and renewable curtailment is around 520 megawatt per week. Shortage hour is 12 hours per week. But after implementing this model, forecast driven model, and using the gas turbine and BAS, our grid import falling from 4,300 megawatt hour per week, which is reduction of about 40%. Renewable curtailment reduces to approximately 160 megawatt hour per week. Export to local grid increases to around 340 megawatt hour per week, and the most important thing, shortage hour reduced to 0. So here, and the other thing is we also able to reduce the carbon dioxide emission approximately 35%. So in the next slide, we will see the cyber security result, and the cyber security testing was conducted across 12 threat categories, including false data injection, reply, denial of service, man in the middle, and others. And our IDS achieve strong performance. Our precision value is 92%. Recall is around 90%, and F1 score is 91% with detection latency is around 1.2 seconds. And to ensure resilience, the system automatically trigger between safe island and lockdown sequence. In safe mode, full grid connectivity is there, and continuous IDS monitoring and conventional interlock ensure secure operation. And in the island mode, it enter during moderate cyber anomalies such as fault data injection or replay attacks. The site disconnects from the grid and operates on local resources, which is Honeywell 16 and our battery energy storage system and PV wind if available. EMS switches to conservative dispatch using BAS for rapid frequency response, while the turbine ramps to meet demand. If demand exceed load capacity, stage load shedding is applied to maintain stability. And we have other mode, which is lockdown mode. It is activated when a severe threat is confirmed. External interfaces are isolated, automated optimization disabled, and emergency deterministic emergency dispatch is used. Only essential service of 15 megawatt are maintained. Critical process line, utilities backbone, safety and control systems, cyber security appliances, emergency power, and critical IT servers, non-essential industrial loads are discharged. And we have backup also for this lockdown mode. So our base alone can sustain 4 hours, and Honeywell 16 can continuously sustain essential services subject to availability of green hydrogen, with base reserved for transient and contingencies. And going through the conclusion of this work, this forecast-driven energy management with battery storage and green hydrogen-based gas turbines significantly improves cost, emissions, and reliability. Grid dependence is reduced, curtailment is minimized, and outage risk is eliminated. Cyber-secure intelligent layer control ensures safe operation under attack conditions. This work sets a pathway for industrial microgrid deployment across national manufacturing parks and global energy transition initiatives. So next step for this model includes hardware validation and pilot deployment at Sipcot Nanguneri, full techno-economic and life cycle emissions analysis including hydrogen pricing and BESS aging. Integration with green hydrogen hubs planned by Government of India, field validation using real dynamics and real-time cyber attacks simulations. So thank you. Coming to the end, I am saying thank you. I would like to sincerely thank my organization Baker Hughes for its vision on net zero carbon emissions, electrical initiatives, and for giving me the opportunity to present this work here. I am grateful to the panel and audience for their patience and attention. Finally, extend my gratitude to India Energy Week and Ministry of Petroleum and Gas, Government of India for accepting our research and providing such a wonderful platform for early career professionals like me. Thank you so much.
Thank you, Saket. Again, an interesting presentation and completely aligned with the approach you have taken. So good luck with improving the modeling accuracy on that. Our last presentation is with Undavalli Sai Venkata Sitaram from IndianOil. And again, we talk about electrical integration.
Thank you, sir. Very good afternoon, delegates. Myself, I am Sitaram. Currently, I am working with IndianOil as a manager in pipelines department, looking after pipeline maintenance. And the topic I am presenting is entirely different from my work culture. Today, I am going to discuss about advancing electrical architecture in wind energy. In this, I am going to discuss about the evolution of wind generator technologies and why adapting the new changes like making hybrid systems and adapting hybrid advanced power electronics and involving AI will make wind energy more reliable and grid supportive, and it will help India in its net zero transition. Going into the topic, let us have a look at the renewable energy goals and role of wind. India renewable energy goals. India has set an ambitious goal of achieving 500 gigawatt through installed non-fossil fuel capacity by 2030, and India is leading its non-fossil fuel renewable capacity by already it has reached 230 gigawatt, out of which majority is solar, approximate 120 gigawatt, and 54 gigawatt is from wind. And India has also achieved its COP26 target of reaching 50% of its installed capacity by before the target dates. And wind energy role and potential. Wind energy contributes to over 54 gigawatt of installed capacity, making the fourth largest in terms of wind installed capacity after China, US and Germany. As per MNRE in India, wind has a potential of reaching up to 300 gigawatt to 1100 gigawatt. It is again subject to the height of the towers that we are going to install in future wind turbines. With such potential in future, wind energy plays major role in renewable energy, and it also plays making grid reliability stronger on renewable energy. What are the technological modernization that we require? Technological modernizations like establishing hybrid parks, as most of my colleagues already discussed. We should integrate wind with battery, utilize scale batteries and solar. And next, using advanced power electronics, switching from conventional IGBTs to advanced silicon carbide inverter technologies. And AI, like already one of my panelists told, adapting digital twin technologies will make wind energy dynamic and grid supportive, acting like a conventional synchronous generator that reacts to the grid faults and everything. What are the grid integration challenges? Today, most of all the conventional wind turbines, all the wind turbines which are existing in India operate on a grid following mode, which is rather like we have an energy source, it it just checks the grid voltage and frequency, and based on the availability of the energy, it will inject the current into the grid. And we have to change that, because in future we are going to more, as we are approaching net zero, we will be more reliable and renewable energy, and the grid should be more on renewable centric rather than conventional synchronous generators, what is present coal thermal plant centric. So to achieve that, we need to change the major grid operating mode of the wind turbines. Getting into the different operating modes, there are two type of operating modes. One is grid following, and the next is grid forming. As you can already see, grid following is nothing but the inverter which is installed in the near the wind turbine will check the grid voltage and frequency and aligns to it and injects the power. The grid forming is the inverter is capable of generating its own voltage reference and frequency reference, and it can take the load upon on itself. Rather, it is dependent on, it is not dependent on some grid to connect it on. And you can see some of the major features like black start capability, which is very important for grid forming generators, which are not available in all the conventional wind turbines or wind generators we are using in today's technology. What changes to be done to make the present grid of the present wind turbines into a grid following into a grid forming rather than grid following? Before that, we need to understand a little bit of evaluation of generator technologies. First, the initial commercial fleet, the first wind farms are equipped with squirrel cage induction generators, which are nothing but a squirrel cage induction motor which operates above the rated speed and produces energy. The major drawback in this is it only operates and generates energy at the rated speed, that is constant speed, and it draws the reactive power. As wind is intermittent, we all know, it is unable to capture the power during the intermittent winds. It only captures the power at the particular speed. So we need to get rid of this, and we need a technology which allows us to capture the power at different variable speeds, and that is the advancement we get with DFIG. DFIG is nothing but doubly fed induction generator, in which we place a partially rated converters in the rotor winding, which enabled it to control the reactive power and generate the energy at variable speeds that are less than the rated speeds of the generator and more than the rated speeds of generator. And as on date, 70% of the existing wind turbines in India are DFIG model only. But what are the drawbacks in this? DFIG, it is directly connected to the grid. The stator is directly connected to the grid, which makes it a fault prone. In case of any grid instability, that generator directly disconnects from the grid, and it won't support any fault right through, and it further increases the grid instability. Because of this, we need a requirement of full converters rather than using partial converters, which will separate the electromechanical parts of the wind turbines from the grid in case of the grid instability. And from there, we reached the next generation technology like PSMG technology with full converters. PSMG, permanent magnet synchronous generators using full converter. By using PSMG's efficiency has improved a lot, because they use permanent magnets, rotor excitation losses, everything got decreased, and as it is enabled with full converter, there will be it can just scale up the frequency as it is equipped with full converter. So we can reduce the the gearbox can be removed, and the mechanical maintenance got down. And it also supports, as it is equipped with full converter, it also supports fault ride through and frequency support, it also supports the grid forming operation. But although it accounts to 30% of the current fleet in India, although the full converter PSMG technology are technically capable of grid forming, but they are operated as grid following due to the limitations like energy buffer. In grid, as grid is intermittent, to be a become a grid forming type, we should also have energy buffer in case of any more energy requirement. The system should able to be supplied. So we will meet this energy buffer by hybrid parks, like integrating wind with BESS battery, utility scale batteries, and solar, everything. Next, one of the research stage emerging alternatives are SRG, switched reluctance generators. They are in prototype development stage, which will be a futuristic option because they will eliminate the requirement of permanent magnets. The rotor is only of proper steel. By eliminating permanent magnets are mostly made up of rare earth materials. With this, we can also align our dependency on rare earths. Foreign countries will decrease. It also aligns with our mission like Atmanirbhar Viksit Bharat. And major developments in this SRGs is it operates on the rotor positioning sensors. It will generate power based on the rotor position and current excitation. Those technologies are in pilot phase. Once these get developed, by replacing these SRG alternatives in the current existing fleet, it will be a huge boost to the existing wind power. Next, a small view like different types of wind turbines we have, and what is the approximate share they are having in India, and major installation time. Only the advanced type for the last one, PSMG plus full converter plus hybrid parks, which we are called, they only offer the grid forming. They are less than 1% in India. Next, going to the role of power electronics in making the wind energy a grid forming capabilities. We used to have a conventional IGT based transistors in the inverters. Now we have to switch to silicon carbide and gallium nitride, which offer high switching frequencies and better thermal performances, which will reduce the filter sizes. Because of high switching frequencies, the harmonics will get reduced and the filter sizes will reduce. Overall, the component size will reduce, which will be helpful in the offshore sites. And full-scale converters electrically decouple the turbine's mechanical system from the grid. This decoupling enables grid forming operation, which we want to achieve, and with the virtual synchronous machine control. Modern wind turbines can provide synthetic inertia, frequency support, and damping during grid disturbances with the help of these full-scale converters. Advanced converters also enable black start capability, allowing wind farms to actively contribute to the grid restoration and stability. Along with this, there are other benefits using full-scale converters. Are modern wind turbines with full-scale converters provide reactive power control similar to STATCOMs, statutory synchronous combiners. These converters enable fast injection or absorption of reactive power, improving voltage stability. This functionality ensures the compliance of India's CEA code, like maintaining 0.33% of rated capacity reactive power injection or absorption at the point of connection. Reactive power flexibility, which is especially critical in weak grid regions like wind-rich regions like Tamil Nadu and Gujarat. By dynamically managing reactive power, converter-based wind turbines reduce curtailment risks and enhance overall grid reliability. Hybrid control strategies allows simultaneous operation of active power and reactive power, improving operational efficiency. These controls support voltage recovery during grid faults, increasing system reliance. Let us have a look how to use AI and digital twin technologies to improve wind performance. AI and digital integration. A digital twin technology is nothing but digital twin uses a real-time sensors data to virtually replicate wind turbines and optimize performance, enable early failure detection by continuously monitoring operating conditions, AI-based predictive maintenance forecasts component issues, reducing unplanned downtime. Use of autonomous drones with computer vision inspect blades and towers, lowering inspection time and cost. Fleet level optimization and repowering, combining weather data, improves energy yield and output balancing. The major change that we have to do is establishing hybrid parks, not establishing individual wind turbines. Along with, we should integrate them with utility scale batteries, and if possible, solar parks also should be placed nearby. Hybridization and storage integration. Hybrid renewable parks will integrate wind, solar, and utility scale storage batteries to maximum energy utilization. As on today, wind utilization capacity utilization factor is only 25% per year. Out of 54 gigawatts, we are able to use only 16 gigawatts. This storage integration will help improve the capacity utilization factor beyond 25% by capturing surplus generation instead of curtailment. The major problem is during the night times the wind will be more and the generation is more, but the load is less, and as they are all grid forming, it leads to the curtailment. The wind turbines will be removed from the grid to balance the voltage and frequency. To avoid this and utilize that energy also, we should integrate them with batteries so that the excess energy will be stored and during the peak hours it will be distributed. And it also supports the Indian decarbonization transition, enabling a gradual shift from coal to flexible storage assisted clean energy. With this, there should be some strategic recommendations from my side, like policy future outlook. Adopting grid forming converters and wide bandgap power electronics is essential for modern wind projects, which makes wind energy more reliable and reduces dependency on coal, as future is morely centric towards renewable energy. If you want to more reliable on renewable energy, it should be a grid supportive and grid forming rather than grid following. To that, we should adopt the grid forming converters and wide bandgap power electronics. Domestic research like prioritizing indigenous converter design, effective magnets, digital twin platforms. Policy making the operators like giving incentives for those operators who are providing these features from their wind farms. These help India in achieving the strategic leadership in the renewable integration. And I just also want to share some of the innovation that in the world in this wind, which is an airborne wind system. This China has recently commissioned this in January. It is a 3 megawatt helium lifted wind turbine. The major benefit is there will be reduction of all the infrastructure, like there will be no towers, nothing. It is lifted to a height of 2000 meters using cables, and it consists of 10 to 12 small turbines, and upon commissioning it has generated 385 kilowatt power, and with the use of electrical cables the power is generated. Such type of technology should be adopted across the world because they help powering the remote locations morely usable and reduce the infrastructure costs. With it, I will conclude. Thank you.
Thank you very much. All right. If not, I would like to say thank you, gentlemen, for such an enlightening session. Let's have a round of applause for the people.